This actually first folder we're not going to go through, but I'll just show it to you. Several years ago, this calculator does all this integration for us. And so I actually went through and set up the integrals for all of the standard shapes on your crib sheet. This the rectangle, the triangle, the half circle, the quarter circle. And so you don't need to do that for your test, but if you're really looking for a good time, this is setting up the calculation for all of these different shapes, like in terms of A, B, and H, and so on and so forth. And I just stuck that in there just for fun. And that's in that first folder. So centroids by integration. So first of all, these common shapes. We're going to be referring to this in several of the problems that we worked today: the triangle, the circle, the half circle, quarter circle, and the arcs or the lines, the quarter circle and the half circle. And what I usually do when I'm starting to work a bunch of centroids problems, I'll usually, even though I have the tables in front of me, I will usually write out the formulas one more time, especially the harder ones like the line centroids and then the quarter circle and half circle. I usually write those out. And so the quarter circle and half circle, the centroid is 4r over 3 pi. And then the half circle, it's the same way, 4r over 3 pi. But the arc, or the line, the centroid is 2r over pi and 2r over pi. And so to just be sure those are crystal clear in your brain, it's pretty helpful. So what is a centroid? So you've seen these definitions. So the definitions, if you have a given area in an XY coordinate system, the x centroid is defined as the integral of x tilde dA divided by the integral of dA. And the y bar for that area is the integral of the area of y tilde dA divided by the integral of dA. So the denominator is obvious, it's just the area. But the numerator is actually a moment equation. It's a moment summation. You're taking the moment of an area about the axis of interest. And so if x bar, you're taking the moments around the y-axis. And the distance from the y-axis to the centroid of the area is x tilde. For y bar, you're taking the moment of the area about the x-axis. And the y tilde is the distance from the x-axis up to the centroid of your dA. Now there's 3 different dAs that you can choose. You can choose, in general, you can choose a horizontal dA, a vertical dA, or a dx dy dA, and then use a double integral. In general, you could do all 3, but here in a little while, I'm basically going to argue that to me the best approach is the double integral. Are you guys comfortable doing the double integral? Because that's the best, because here we're doing centroids, but later we're going to do moments of inertia, and the integrals of moment of inertia is the integral of y tilde squared dA, or x tilde squared dA. And if you're using a double integral, it's the same integral. You're just interchanging an x or a y, and it's very easy. And that's in chapter 10, so you're not there yet. But the other thing with chapter 10 is, in general, I'm getting ahead of myself, but even though you could choose any dA, it's best, well, I'll show you, since I'm talking about it. So what are your best choices of dA? And basically, the double integral is the best because it works for so many different cases, and for chapter 10, moments of inertia and product of inertia. However, the next easiest, and also pretty good, is to choose, if you're dealing with y bar, use a horizontal element that's parallel to the x-axis, and so your y tilde is just y. And if you're finding x bar, don't use the same element. For x bar, use a vertical element where the distance from the y-axis to the centroid here is just x. That's easier. And when you get to moments of inertia in chapter 10, it becomes even easier to do that. So an element parallel to this axis, an element parallel to this axis. That's the next best approach. And I'll show you some of the other approaches, but they get harder as we go on. Does that make sense to you, to choose those? Back to what a moment of inertia is. So again, the numerator is a moment equation. And the way these equations are defined, these are defined for your area that's like out here somewhere, and then you've got an x and y axis here where they're distant from one another. But what does this equation look like if instead of using an x and y axis here, you're evaluating that integral about the centroidal axes? So what if you already know the centroid and you know that there's an x prime axis through the centroid and a y prime axis through the centroid? What does this numerator look like? And the result of that is basically 0. So the numerator of this x tilde dA is the moment of this area about the y prime centroid. And so exactly half of the area is on this side, exactly half, well, it's not exactly half of the area, it's the moment of the area on one side is equal to the moment of the area on the other. And so the sum of x tilde dA is 0 about the y-axis. And about the x-axis, the numerator of this guy, the y tilde dA, the moment of the area that's above the x-axis is exactly equal to the moment of the area below it. And so they balance one another. The top area is positive, the bottom area is positive sum of y dA, and then the bottom part is negative y dA. They cancel one another out, and so those numerators are 0. And so that's a property of those centroids that we actually use later in the class. So in other words, if you have a plate with a uniform mass and you put a pivot at the centroid of that plate, it will balance on that point, because the moment of the weight on one side is exactly equal to the moment of weight on the other. Same is true with a rod, same is true with a solid, as long as they have uniform density. Now, occasional conceptual question just shows up from time to time, is what if you have a composite shape that are made of different materials with different densities? Is the mass center the same as the geometric center? And the answer of course is no. So as long as a composite shape has got, the shapes are all made of the same material density, then the mass center is exactly equal to the geometric center. But if some of those pieces have a different density, again, then the geometric center is not the same as the mass center. So, when I say centroid, I mean mass center, geometric center, the whole 9 yards. And for most cases, that's true. But if you get different materials, they're not the same. Just keep that in mind, because that conceptual question sometimes shows up. And I think it's kind of evil, because I never talk about it. I don't typically talk about it, and your book doesn't talk about it, and you don't have problems in your homework like that, but it's just like that would show up sometimes on the test. Some examples of problems where, again, the moment on one side is exactly equal to the other. One interesting example is the population center of the United States. And so literally, if you took a map of the United States and put a point at every place where a person lives and balance that map, the population center of the United States is here in Missouri. And so it's like near Hartville, Missouri, which is like 40 miles south of Lebanon, and it's about 85 miles south of Rolla, Missouri, and it's about 30 miles east of Marshfield. Anyway, so it's actually in Missouri. And so that's a centroid problem, applied to people. Now, again, where each person counts as a unit. We're not counting the weight of every individual person. When you get to mechanics materials, in mechanics of materials, if you look at the cross-section of a beam, there's a bending moment. And we didn't talk about this with internal forces, but this bending moment is a resultant of a stress distribution that exists on the face of that beam. And so, and again, this is just a resultant. If you cut that beam open, you're going, where's that bending moment? Where's that resulting bending? It doesn't exist. What there is a stress distribution across that entire face. And that stress distribution is signified by sigma, which are bending stresses. They're normal stresses because they act perpendicular to the cut of the beam. And the top of the and a beam that's normally loaded from the top is going to bend downward. And so the top fibers of the beam are in compression. The bottom fibers of the beam are in tension, which it stands to reason that somewhere in the middle of the beam, those stresses are zero. And that's called the neutral axis. The centroidal axis is called the neutral axis. And so above that neutral axis are the fibers are in compression, and below that neutral axis, the fibers are in tension. So I say that to say this. When you get to mechanics of materials, you're going to find centroids of beams all the time, over and over and over again, because you have to know where the neutral axis is. And so that's an application of centroids. In dynamics, when you look at the dynamic, the motion of a rigid body that's got some dimensionality, that in projectile motion or whatever motion that body is in, the mass center of that body tracks along its path. And the body might rotate about that mass center. But for example, a BMX rider on a motorcycle, you've got, and they might be doing flips or whatever else, but once that BMX rider leaves the ramp and is flying through the air, the centroid of the combined center of gravity of the rider and the motorcycle, that mass center follows a perfect parabolic arc from projectile motion, basically. But it's the composite centroid of that person. It applies to a ski jumper, spacecraft, satellite, planes, airplanes. The center of gravity, obviously, of an airplane is super important, and the balancing of the load, the cargo of the plane, plus the passengers of the plane, plus the plane itself. The center of gravity is really, really important. And so there's lots of applications where center of gravities or centroids are pretty important. So that's what a centroid is. And if we integrate for them, again, I told you about the DAs. Let me just show you an example by integration. So this is a real simple example from your book, and just a very simple parabolic curve. Y is equal to x squared. We're looking for the centroid. We're looking for the x bar and the y bar, and again, you've got 4 different methods you can choose from. You can use a double integral with a dA that's dx dy. You can use a double integral where the dA is dy dx. You can use a single integral with a vertical element, or a single integral with a horizontal element. And so in each case, it's the same integral setup. So it's still the same setup. So the setup is still, you still have x bar is equal to the integral over the area of x tilde dA divided by the integral over the area of dA. But the question is, what is dA? What is x tilde? And for each case, that's going to be slightly different. For a double integral, the dA is always going to be dx dy or dy dx. And the x tilde is always going to be x, and the y tilde is always going to be y. That's what makes the double integral so easy. It's always the same setup. Super, super easy. The horizontal elements, let's see what I got. What's next? So a vertical element, once you draw the vertical element, so a vertical element is dx wide. And the top of the element is y, and the bottom of the element is actually 0. But because it's dx wide, you have to express y as a function of x, and so you plug that in, and so your dA then becomes x squared dx. Your x tilde is the distance from the y-axis to the centroid is just x. But the vertical y tilde, the distance from the x-axis to the centroid here, is 1/2 of y. Okay, so you have to be smart enough to know what you're doing for the vertical element. For horizontal element, if you take the horizontal element, now your dA is 1 minus x times dy. But then because you're using the dy, you have to express the x in terms of y. And so if y is equal to x squared, then x is equal to the square root of y. So you have to plug in square root of y here for x. So your dA is actually 1 minus the square root of y dy. Your y tilde, which is the distance from the x-axis to here, is just y. But the x tilde is the average of this right. I call it x right and x left. And so the x right edge here is 1. X left is x. And so the average of these two goes, so your x tilde is the average of, so it's x plus half of x plus 1. Oh, no, I guess it's 1 minus x divided by 2. Yeah, so the length of this dA is 1 minus x. And so half of that is 1 minus x over 2 plus x. Can you see how much harder that is than a double integral? So a vertical guy for parallel to the y, and this guy for parallel to the x is pretty easy. But whenever you have to get the average of the two, it just gets messier. The setup gets messier. And here below, I just go through. So here we basically intuit the terms, and the rest of this problem I actually work it, and I'm not going to go through that for you. And I show you how to do the TI-89. You should know how to integrate with your. Do you all know how to integrate with your calculators, either with your Inspire or your 89 or whatever calculator you have? You should know how to do that. I give you the keystrokes for the 89, and it's very similar for the Inspire. So that's a simple example where an area touches an axis. But again, and I show you every possible approach, but some are easier than others. And so part of the goal is being smart enough to know what's the easier way to do this and not the harder way on a given problem. Here's another example, which is an area between two lines. And so this is an area between two lines. And so you've got the same three choices. So you have a horizontal element, you've got a vertical element, and a double integral. Again, the double integral is the easiest because your dA is still dx dy or dy dx. X tilde is still x, y tilde is still y. Easiest possible setup. And then your numerators or your limits basically are going from the one curve to the other, and then from 0 to 1. And so the double integral is a pretty easy setup. The single integral for a vertical element, so now it's dx wide, and I call this y top, and I call this y bottom, but because it's dx wide, you have to convert the y top to an x, and you have to convert the y bottom to an x. And so you have to come up to your functions, and y is already given as 2x, and this y top is the square root. Y top is the square root of this guy, which is the square root of 4x, which is 2 times the square root of x is y top. And so so once you get these guys in terms of x, then your x tilde is still, because it's a vertical element, your x tilde is still x, but your y tilde is the average of y bottom and y top. And so it's y bottom plus y top divided by 2, where you plug in your functions here. And then you have a complex dA, you have a complex y tilde, and then you have an x. And so now you have an x times a dA, which are more complicated than the double integral. For the horizontal element, I guess that's the x numerator, yeah. But the horizontal element is dy thick, and so you got an x right and an x left. You have to convert these to the y values to correspond with the dy. Your dA is x right minus x left times dy. Your y tilde is just y, and then your x tilde is the average of these two, which is complex. So if you use a vertical element, just use it for the x value, and so you're avoiding this guy. And if you use a horizontal element, just use it for the y case, so you're avoiding this average for the x. So there's just some approach. Theoretically, in a perfect world, you should know how to set up all of these different cases. You're not. That's why I did it for you. But be smart enough to know what's the easiest case. What are easier. And then I basically go through all this setup. I work all the examples for you and show you how to do it on your calculator. So questions on integration. What I will say on your test is, and one of these examples we'll see here in a moment, is that we'll get to it. It's not uncommon for them to, the question is just the setup of the integral. It says, okay, this is the area, you're going to use a horizontal element, which is the correct setup. And so you're not actually calculating, you're not evaluating the integral. All you're doing is looking at the choices of the element. And so you need to understand what, for a horizontal element, what a dA looks like and what the x tilde or y tilde looks like. And so you'll see that here in a moment. So the other issue that you run into is the way these are written. It's easy to convert the y in terms of x or the x in terms of y. But what if you have a function here for one of these functions where y is equal to x squared plus 2x plus 4? You can't get x in terms of y. It's just not possible. And so when you're looking for methods to choose, you can't choose every possible dA. You have to choose one that works. And double integral would work, and some others work fine. Like for example, the vertical element would work where you're using a dx, and the one y is a function of x which works, and the other y is a function of x which works, and so vertical element would be fine, but a horizontal element would not work because you can't convert the x back to y. And so, but having said that, there have been exams in the past that one of the functions looked like this, that was impossible to set up other than using your calculator. And that person who did that is still teaching statics today. I'm just saying. And so it's possible that the function may not be this clean, and really you have to use your, and you can do it on your calculator, but as long as you know how to use your calculator, that can work. So that's integration. Question?